We are going to move to the third presentation by Wesley Angelino de Souza from Federal University of Technology from Paraná, Brazil. And then is the design of the digital controllers for grid-connected voltage source converter operating as voltage or current source. The floor is yours.
Thank you, Professor Michele. I have to start to say this work belongs to Claudio Francisco Nascimento. He's a professor at UFSCar and made this work at the Padova University, Universidade del Studio Padova. So I will try to show you this work. So let's go. As yesterday, Professor Luis Carlos told, small is better. So we'll try to start this way. We have industrial, commercial, residential applications that we have using now. Some inverters, generators, etc. So have a grid-connected voltage source converters, and this is increasing all the time. In this way, we have a conscience that power systems are changing. It's important to create some techniques, some models, some controls, and one of these is GC-VSC. It's a grid-connected voltage source converter to create a grid following, a grid forming technologies, models to operate in the system. So, first of all, we have to try to create this model, this basic model, to switch with the grid. So we have to create a control here, and in this work, it's proposed a deadbeat and a PR with resonance. So it's a control technique. That we have to look the voltage, the frequency, the active power, reactive power. It's important to create this kind of model because we have a growing application of digital controllers, and it's important to say also it's evolution of the work made for the group in the Padova University that they used the PI with that beat, and Professor Claudio put the resonance here also to create the following mode at the grid. So this work tries to create a design of digital controllers applied to the single phase. So this purpose is using all in one phase, but it's possible to reply and use in three phase with 3 or 4 wires also. So here we can see the modeling of the system. We have here the voltage source controller, the filter here. We have loads over here, and the impedance, and the switch mode with the grid. So these are the parameters you can find here, and it's possible also to use this method in the island mode. And the control is like this. The forming mode is here. It's using the deadbeat for the voltage and for the current here, and this current and the final of the VSC come back to the forming and also come to this control in the grid following mode. So we have switches here, control switch here, to follow the following mode, the current, the voltage, and the forming to form the voltage and current also in the situation of island, for example. And the results was made using MATLAB SIMULINK. So here is simulation. In the final, I will try to say about the future works. But in this moment, is using all simulations to verify the effectiveness of the controller. So we have some situations. We have to account the single phase of the value of the voltage is 230 volts, and the frequency of the grid is 50 hertz. Here, the first test, it was used grid following mode. It starts very well and near to 42.5 milliseconds. The voltage goes down 20%, and the dynamic of the system show here that it's pretty good. Come back to the reference after less than 10 milliseconds. And here we have some comparative errors about the reference and the model, the grid current in the reference. The values goes the error so little here, and the value of the total harmonic distortion is also so little here for the current mode, and the voltage also is 0.35% of the total distortion. And here is the same situation that I put in the last slide, only to check the current error. And here, the part of the reference, you can see the digital switching, because the resolution, yes, the resolution made this kind of noisy. So, but it's okay because the current, you can see that follow very well also. Here, we have the reference voltage and the moment at 37.5 milliseconds. We have the grid forming and grid following. In this moment, we have a disconnection of the grid, and after you can see here that the controller can follow the grid in the fast way also here. So you can see that in close to 5-6 milliseconds, the grid was followed very well. And here, you can see the error here also with the two here with this noise, but it's only switching and also the digital controller, and the error goes in the delta of 8 volts. Sorry, and here you can see the moment of that have a switch connected here to a new load, and the current go very well out in this situation too. Here is the same way, but now we have another load here. In this load, in the relative way, affects the systems, but the reference here is following very well also. And the final here, the current error is very good, and for the situation with a grid error of 1.07%, the current phase is 0.9 degrees. The voltage error is almost not significant, is 0.01%, and the phase error for the voltage is 0.45 degrees. So the digital-based controller was proposed here. We have relative errors of almost perfect value for the voltage, for the current on an error of 3.67%. It works part of research, as I told for you. It's the intention of the authors is to use the harden the loop and create real scenarios for implementation to validation, because this error is almost zero, but in the real world, it's possible to have the same value. We don't know, but we have to try in this step to use the harden loop and also to create a three-phase controller. So thank you for the attention. I will try to respond if I can. Okay, thank you.
Thank you for the nice presentation. So any questions?
Thank you for a nice presentation. If you are successful testing your approach with the hardware in the loop, then I'm curious, what would be the next step in order, for testing in real life?
After the use of hardware loop only to test if the real scenario can create a good interface with this controller and the real world, but it's hard to say in the hardware loop the relief. But after we can try to use DSP, digital signal processor, to validate the model also.
Because I'm thinking sometimes when you want to try to get things out and try it, I was wondering, do you have any larger test facility where it actually would be possible to run it like in a microgrid or something to see if it would really work as you expect it to?
We will try to use a smart grid, microgrid also. So we try to validate the first step only to create this grid forming way, and after we have to know about the different loads. We have only use the resistive load here, so it's not the real world. We have to check the nonlinear loads and reactive, also capacitive. So the expectations, I think the grid voltage, the grid error goes up, it's almost zero. But Professor Buzo already tried to using DSP with grid values, so we have the same expectation.